Okay, so now we're going to continue our conversation in section 8.1 about our 4 different pieces of our hypothesis testing. So far we've talked about our 2 first steps. We've talked about our pair of hypotheses for our first step and our preparation for our second step. In our third step, we're going to look at some computations. Right? So as we're going through this third step, we're going to compute our observed value that we're looking for, which is going to be a z-score, although it's going to be a slightly different z-score formula than we found before. And then we are also going to find our p-value. In order to find our p-value, we're going to use StatCrunch. So our first definition here is that of a test statistic. So a test statistic compares the real world with the null hypothesis world. Right? The test statistic compares our observed outcome with the outcome we would get if the null hypothesis is true. If the null hypothesis is true, then our z-statistic will be close to 0. And that should make sense because if we have a z-value close to 0, it's close to our mean. When our test statistic is far away from 0, right, so it's far away from a value we'd expect, right, then we're going to reject our null hypothesis and conclude that the evidence supports the alternative hypothesis. The further away the z-statistic is from 0, the more the null hypothesis is discredited. And this shouldn't be any big surprise. As we were going through stuff in Chapter 3, as we were going through stuff in Chapter 6, we talked about things being unusual if they had a really large z-score. And if they had a z-score more than positive 2 going in the right direction or negative 2 going in the negative direction. So as we're thinking about these, what we know about z-scores in relation to our mean is still very consistent for these problems. All right, so what we see here is our formula for our z-statistic. It does have a familiar structure. We are taking our observed value minus our null value, and we are dividing it by a standard deviation of sorts. We're dividing it by our standard error. So before we saw z-formulas that were x minus x bar over our standard deviation. This time we're going to use our p hat minus our p sub naught divided by our standard error. Now the only difference is here, our standard error is a more complicated formula. It has that square root in it. So as we're calculating these by hand, more often than not, we're going to use this latter form of our formula to come up with our test statistic. All right, so in 2001, the Gallup poll reported that 12% of Americans were cool skeptics who reported worrying a little or not at all about global warming. In 2014, 25% of those responding to the poll classified themselves as cool skeptics. Assume that the sample size for 2014 was 500. Can we conclude that the percentage of Americans who identify themselves as cool skeptics has increased since 2001? So the first thing we're going to do in any of our problems is we are going to come up with a pair of hypotheses. Right? So our null hypothesis, right, again, always has an equal sign. Right? And we're always going to go to the beginning of our problem. We're always going to look for that p naught value, that original percent. So our original percent is 12% of Americans reported that they were cool skeptics. So our p is going to be equal to 0.12 for our null hypothesis. Our alternative hypothesis, right? P, now we have 3 symbols to choose from, either greater than, less than, or not equal to. In this case, we're looking at the word increased, so that's going to mean greater than 0.12. So as we progress through all these problems, before we do anything, first thing we're going to want to do, generally speaking, is think about our pair of hypotheses. All right, so now we're going to continue this example at the top of the next page, and we are going to find our test statistic. Right, so when we're finding this test statistic, we're going to use this formula with the square root that we see here. Right, so our p hat is the other percent that's mentioned in our problem. So if we look back at this problem, we see that our p hat is going to be this 25%. Right? So we're going to do 0.25 minus p naught, that was our original percent, that was our 12%. So again, that's our p naught, the 25% is our p hat. Right? And then we're going to divide it by our square root part down here. All of these are p naught, so all of these are using the 0.12. And then our sample size is 500, so our denominator of this square root portion is going to be 500. Now, as you're plugging this into your calculator, you do have some options. You can do some rounding. You can plug it in all at once. If you plug it in all at once, make sure that you're using parentheses correctly. Make sure you kind of go through and double check. Take the examples that you see in your notes. Make sure that everything matches up correctly. If you do want to do some rounding as we go, so in this particular case for this example, 0.25 minus 0.12, or 25% minus 12% gives us 13%, 0.13. Right? And then in the bottom, right, I'm going to leave my square root here for a second, and I'm going to keep a bunch of decimal values here. So my 0.12 times 1 minus 0.12, our complement, divided by 500, is going to give us 0.00021112. Right, so if you do want to do some rounding, if you're plugging it into an alternate type of calculator where you can't plug it in all at once, just make sure in your square root you keep as many decimal places as possible. We divide this out, then we're going to get 8.95. So thinking about this, our test statistic compares our observed outcome with the outcome the null hypothesis said we should see. Right? So our test statistic is that z equals 8.95. Right? Which, thinking about z-scores, right, that is an extraordinarily high z-score. Right? So we're going to say this means that while the null hypothesis claims a proportion of 12%, the observed proportion was 8.95 standard errors higher than what the null hypothesis claims. A z-score of 8.95 is definitely very unusual. Right? We don't expect to see z-scores that are that high. Right? So this idea of our z-score, our test statistic that we're looking at, it is going to be a value that we're going to compute as we're going through some of our problems, but it's also going to tie directly into our next idea of our p-values. So p-values give us a way to measure our surprise. So how unusual is our value? How surprised are we at this z-score for this previous example where z is 8.95? So if we see something that is unexpected, right? If we are surprised, if we have an extremely high or low z-score, then we should doubt our null hypothesis, right? If we are really, really surprised, then we should reject it altogether. Right? So what we're going to do is we're going to use another mathematical value, excuse me, called our p-value to help us make this decision above and beyond just looking at our z-score. So our p-value is a probability. It gives us a way to numerically measure our surprise, just like our z-scores gave us a way earlier in this course to measure how unusual a value was. If the null hypothesis is true, the p-value is the probability that the experiment was repeated. Our test statistic will have a value as extreme or more extreme than the one we actually observed. So what this means is small p-values, p-values that are very close to 0 means we are going to be really surprised. Large p-values close to 1 means we are not surprised at all. Right? So as we're looking at this, this phrase that's kind of in that second bullet point there, right? What does that mean? If the null hypothesis is true, The p-value is the probability that if the experiment is repeated, our test statistic will have a value as extreme or more extreme than the value that we actually observed. Right? So this is saying that if we were to repeat this experiment, would we likely in a way get similar results? Right? And that's what we're looking at here. So if we have a very large value close to 1, right, we should expect that we end up with something similar, something that's not surprising, means our null hypothesis is probably valid. If we get something close to 0, that means that we're going to be surprised. It means that our z-score is going to be either ridiculously high or ridiculously low. It means that we are really surprised about the values that we are getting. It means that there is a good chance that our null hypothesis is incorrect and that our alternative hypothesis is actually the one that is true. So as we're going through and we're thinking about these, we've talked a little bit about our one-sided and two-sided tests. So looking at these few different kind of next images at the bottom of this page and the top of the next page shows what our alternative hypothesis looks like in relation to our normal curve, in relation to our z-scores that we saw. So if we're looking at a two-sided test, if we have a z-score that's in our extreme either left or right tails, right, that's when we're going to get a very small p-value. If we look at the examples on the next page, there we have a left and we have a right. Again, what we're thinking about and what we're looking at when we're thinking about our hypothesis test is where are these values landing as far as our tails go. Right, so we're going to use this kind of information to look at our next example. So in the last example, we saw that the Gallup poll reported that 12% of Americans were cool skeptics who reported worrying a little or not at all about global warming. Again, in 2014, 25% classified themselves as cool skeptics. Assume that the sample size for 2014 poll was 500. Can we conclude that the percentage of Americans who identify themselves as cool skeptics has increased since 2001? The p-value is calculated to be nearly 0. Interpret the p-value in context. Okay, so the first thing I'm going to do is I'm going to copy down my set of hypotheses from our last example. It should be example 5 here. All right, so our null hypothesis was p equals 0.12, and our alternative hypothesis was that p was greater than 0.12, right? Had the percentage increased. Our test statistic from our last example, our z-score, z was 8.95, right? And we are told in this paragraph above that our p-value is approximately 0, right? So thinking about the information that was on the previous page, right? Small p-values that are close to 0 mean we are really surprised. And what we're going to end up doing, and we'll see on the next page as well, is we're going to end up comparing our p-value to our level of significance. When we are really surprised, when we are able to do this comparison that we're going to look closer at in the next sample, right? We're going to say this gives us strong evidence to reject the null hypothesis. Right, so the closer our p-value is to 0, the stronger the evidence we have to reject our null hypothesis. So looking at our statements that we have, right, if we reject our null hypothesis, what I'm going to do for now is I'm just going to cross it off. So I'm going to say that we do not think that that is true. Well, if we do not think that that is true based on the information that we have, right, that means that this scenario is the more likely case, right? So since this scenario is the more likely case, this is saying that our proportion has increased, So we conclude that the percentage of Americans who identify themselves as cool skeptics has increased since 2001. So in this case, we're just doing this based off the fact that our p-value is close to 0. In the next example, we're going to give kind of something, a more concrete way of deciding that we want to either reject our null hypothesis or do not reject our null hypothesis. All right, so in this last and final step that we're looking at step 4. We're looking at our interpretation. Out of our entire procedure, this last step is our goal, right? This is what we're looking for. This is the question that we want to answer as we're doing these problems, right? So do we reject or do we not reject the null hypothesis? What does that mean in context of the data and the actual problem that we are looking at? Right, so what we have here, this is pretty much the key for every single problem that we're going to look at in the rest of the section. Right? So using our p-value to achieve a significance, it should be a t, to achieve a significance level of alpha, we are going to reject our null hypothesis if the p-value is less than or equal to alpha, and we are not going to reject our null hypothesis if the p-value is greater than or equal to alpha. Remember, the closer the p-value is to 0, right, if we're thinking of a significance level of 5%, right, if our p-value is less than 5%, right, and then we're going to reject our null hypothesis. P-values close to 0 mean we're surprised. Right? If we have very large p-values, right, we're going to be way larger than our significance level. So if that's the case, we're not surprised. So we are not going to reject our null hypothesis. All right, so in this last example, we're going to start by kind of starting with a summary of different things, kind of like we did with a bunch of examples in Chapter 7, and we will continue to do with examples in Chapter 8. And then we're going to look at output data from StatCrunch, and then make a conclusion based on that. So a student claimed that spinning a coin rather than flipping a coin leads to a biased outcome. If we spin the coin 20 times and see 7 heads, which gives us a sample proportion, a p-hat of 0.35, assume the required conditions are satisfied so that the sampling distribution of the test statistic is approximately the standard normal distribution. Right, so we're going to find our approximate p-value and explain what it means. Right, so our n is our sample size. Right, so in this case, our sample size, we're looking at 20 coin spins. Right, our p-hat is the amount that gave us heads. So our 7 out of 20, right, is going to give us 0.35 or 35% if we divide it out. Right, our null hypothesis, right, is going to be that p is equal to something. Right, so thinking of that, we're comparing this to flipping a coin. Flipping a coin, we have 50% odds of getting a heads or a tails. So our null hypothesis, right, since we're comparing this to flipping a coin has a probability of success or failure, however we want to look at it, of 50%. So we're going to use our p equals 0.50. Right. A student claimed that spinning a coin leads to a biased outcome. We're not necessarily told if it's a greater than or less than case, right? So we're just going to assume that there was a change. So our p for our null hypothesis is going to be not equal to 0.50. So again, we're going to start by writing out the information that we know. Right? So when we're going through these problems, we're going to start by doing this, then we're going to check our conditions, We're going to do some computations if necessary, and or we're going to go to StatCrunch. And the type of output that we get from StatCrunch is going to look similar to this. It's going to give us a proportion, it's going to give us our number of successes, the number of total observations, our sample proportion, our p-hat, it's going to give us our standard error, it's going to give us our z-value, and it's going to give us our p-value. Right? So in our case, our p-value is 0.1797. So what does this mean? So we're going to say the p-value is about 0.18. That tells us that if spinning the coin is fair, then the probability of seeing an outcome as extreme or more extreme than 35% heads is about 18%. So that is what our p-value is telling us. So you might run into a question here or there that asks something about what the p-value is telling you. This example is what you're going to want to kind of refer to as you're thinking about these. Now this last part down at the bottom, this draw and interpret a conclusion. Right? This is, again, the key part to every problem that we're going to see in the rest of chapter 8. Right? So we want to think about how does our p compare to alpha. So we're going to say if alpha equals 0.05, right? Because a lot of times we use 5%. Right? Then our p is greater than alpha. Right? So if we look back up to this guide up here, right, we do not reject the null hypothesis if the p-value is greater than alpha. Right? So since p is greater than alpha, then we would not reject the null hypothesis that spinning the coin is fair. Again, our p, right, is 0.18, our alpha is 0.05, and p is greater than alpha. So notation wise, one thing that I recommend doing, especially as you're going through these problems in your homework or other things along those lines, once you decide whether you're rejecting or not rejecting, go back up to your pair of hypotheses and circle one and cross the other one off. So in the previous example, we rejected our null hypothesis, so we crossed that off and we circled our alternative. In this case, we are not rejecting our null hypothesis. Right? So that is why we are assuming that spinning the coin is fair, right? And we are eliminating our alternative hypothesis. Right? So as we continue to go through the next few examples in section 8.2, we're going to take all of this different information that we saw in section 8.1, all 4 of our different steps, and then we're going to put them together to go through our entire procedure as a whole.